this unit, we will be discussing lines that intersect circles. A learning objective for today is by the end of this lesson, I'll be able to identify tangents, secants, chords, and use properties of tangents to solve problems. Our essential question is, what are the definitions of the lines and segments that intersect a circle? Remember, please try to complete your guided notes, and we are on page 530 of your geometry textbook. And we meet every day, Monday through Friday at 10 a.m. A circle is a set of all points in a plane that are equal distance from a given point called the center of the circle, like so. All these green segments are the same distance from the center of the circle to the circle. A circle with center D is called circle D and can be written as circle D. Coplanar circles are circles that lie on the same plane that intersect in one point. These circles are called tangent circles. Circle R and circle S are tangent circles since they intersect at one point. Circle S and T are also tangent circles because they intersect at one point as well. The interior circle is the set of all points inside the circle. The exterior circle is the set of all points outside the circle. A segment whose endpoints are the center and any point on a circle is the radius. Notice that our radius, we go from the center and we extend all the way to the circle. So this portion from here to here will also be a radius. And if we start from the center circle and go to our left, this will also be a radius. We can also construct a radius like so. And this would also be a radius. A chord is a segment whose endpoints are on the circle. So notice that the endpoints are on the circle. A diameter is a special type of chord that not only are the endpoints on the circle, but it passes through the center of the circle. Again, a diameter is a special type of chord. A secant is a line that intersects a circle at 2 points. Notice that a secant and a chord are very similar. The difference is a secant has arrowheads at the end, which makes it a line, and a chord at the end have endpoints. So therefore, this can be secant if we say line, and it also could be a chord if we let's say a line segment. A tangent is a line in the plane of a circle that intersects the circle at exactly one point, called a point of tangency. In this case, point B is our point of tangency. The tangent ray AB, starting here and going to your left indefinitely, or tangent segment AB are also called tangent. So notice a tangent can be a line, a ray, or a segment, while a secant is always a line and a chord is always a segment. Identify each line or segment that intersects circle L. So notice that we have chords. Our chords have to be endpoints. So the first one we can see is we have J and M. That is a chord. We also have the chord K and M. So those are our chords. Remember, a chord is a line segment whose endpoints are on the circle. A secant and chords are very similar, but the secant is a line that passes through the circle at 2 points. So in this case, JM. That's our line because we see the arrowhead. So notice that we can say chord JM by simply writing segment JM. And for secant, we say line JM by using the arrowheads at the end. Tangent, when we name a line, we want to use 2 points on the line. If we don't have 2 points, we name it by the lowercase letter. So in this case, we'll write out line M. The diameter has to go through the center of the circle and has endpoints on the circle. So it's a special chord that goes through the center of the circle. So in this case, our diameter is the same as segment KM. Our radii will start from the center circle and extend. So we see we have the radius LK, we also have the radius LJ, and we also have the radius LM. So those are our 3. Coplanar circles and common tangents. In a plane, 2 circles can intersect in 2 points, 1 point, or no points. Coplanar circles that intersect in 1 point are called tangent circles. Coplanar circles that have a common center are called concentric circles. Notice here we have a common center. So common center, concentric circles. A line or segment that is tangent to two coplanar circles is called a common tangent. A common internal tangent intersects the segment that joins the center of the circle. This line in green connects the center of the circles. These are common internal tangents since it crosses that line. A common external tangent does not intersect the segment that joins the center of the circles. Okay, so as you can see, this blue line does not intersect this green line, and this blue line does not intersect this green segment. So we have four common tangents, two are internal and two are external. On this particular example, it states, tell how many common tangents the circle has and draw them. Use blue to indicate common external tangents and red to indicate common internal tangents. In this particular case, we have two common external tangents. In order to find the radius of circle R, we will take a look at the circle and count. When we count vertically or horizontally, we will notice that we have a length of 2. We can go diagonally, but unfortunately, we would have to do a lot more work. To find the length of the radius of circle S, we would do the same exact thing and we would get 1.5. The point of tangency is the point in which the two circles meet. So they meet right about here. So that would be -2, 0. And the equation of the tangent line is the line that goes through the point of tangency and only touches each circle at one point. Therefore, this would be the horizontal line, y = 0. You could also state it as the x-axis. Tangent line to circle theorem. In a plane, a line is tangent to a circle if and only if the line is perpendicular to the radius of the circle at its endpoint on the circle. So line M is tangent to circle Q if and only if line M is perpendicular to segment QP. This allows us to use the converse of the Pythagorean theorem. If the sum of the squares of the lengths of two sides of a triangle is equal to the square of the length of the third side, then the triangle is a right triangle. Let's take a look at this example. The triangle below appears to be a right triangle. Tell whether they are right triangles. In this particular one, it looks like it, but since they didn't indicate that this is a right triangle, by using the right angle mark, we can't say it's a right triangle. In order for us to state that it is a right triangle, we would use the Pythagorean theorem. Substitute our values in. Remember, A and B are the shorter sides, and they are interchangeable. We would square, find the sum of 25 and 144, and notice, since a squared plus b squared is in fact equal to c squared, the triangle is right. Let's take a look at another example. Again, this looks like a right triangle. In order to determine if it is, we will use Pythagorean theorem again, substitute the values, and remember, the two shorter sides would be considered the legs. Simplify and add. Notice that 65 does not equal to 64, but they're really, really close. If you're using just your eyes, inductive reasoning, it would look like a right triangle. But since a squared plus b squared does not equal c squared, the triangle is not a right triangle. Let's apply this to the tangent line. Is segment ST tangent to circle P? Unfortunately, they did not give us information to just look at it and say it is. If they were to have this right angle mark, we could say yes it is. Now we need to figure out, and remember that these two sides form the right angle. So the two legs form the right angle. So when we do this particular one, we can't have the right angle here or here, okay? We can't have it here or here. It has to be these two. So these two are going to be our legs, and this is our hypotenuse, which makes sense because these two sides are shorter than the hypotenuse. We would substitute our values, simplify, find the sum on the left side, and notice that they are not equal. Therefore, no, segment ST is not tangent to circle P. But again, remember, this has to be the right angle. If the right angle is here, it is not tangent, or here. The right angle has to be here. So this is our right angle. So remember that. Sometimes they try to trick you by making it work, but the right angle is inside. It's not at the point of tangency. In the diagram, point P is the point of tangency. Find the radius r of circle O. In this particular case, we know this is a right angle because they stated that point P is the point of tangency. Now we can use the Pythagorean theorem. Substitute our values in. R squared is R squared. 36 squared is 1296 is equal to, and now we'll just expand that square. In order to solve for r, we'll subtract r squared from both sides. That leaves us with 1296 is equal to 48r plus 576. Subtract 576 from both sides. We get 720 is equal to 48r. Divide both sides by the coefficient of r, which is 48, and r is equal to 15. External tangent congruence theorem. Tangent segments from a common external point are congruent. So as long as we have a common external point, we can say that these two segments are congruent. This is our external point. This is our point of tangency. This is our point of tangency, causing this segment to be congruent to this segment. Therefore, if segment SR and segment ST are tangent segments, then segment SR is congruent to segment ST. In this particular case, we can see we have the common external point, and we are tangent on these parts. Therefore, this segment is congruent to this segment. So we can set those equal to each other. In order to solve this, we'll set everything equal to 0 by subtracting 48 from both sides. And now we will use the X method, the diamond or X method, whichever way you would like to say it. 1 times negative 48 is negative 48. Two numbers that multiply to give us negative 48, but add to give us 2. That would be negative 6 and 8. Here we would have x minus 6 times x plus 8 is equal to 0. Use the zero product property and simplify. And again, and simplify. Our answers are negative 8 or 6. Let's take a look at another example. In this example, I will demonstrate 3 different ways of solving. Again, we have an external point, point of tangency. Therefore, this segment is congruent to this segment, so we can set them equal to each other. We can subtract 75 to have everything set equal to 0, factor out the 3, and now we notice inside the parentheses we have the difference of squares. This would be 3 times x plus 5 times x minus 5. We can use a zero product property and solve, and we will get x is equal to negative 5 or 5. Let's take a look at it, a slightly different variation. We would subtract 75, but instead of factoring out the 3, since this is in the equation, I could actually divide through by 3. Notice I have the difference of squares, x plus 5 times x minus 5. Use a zero product property and simplify. And the third way. Instead of subtracting 75, I would divide by my coefficient. Now we take the square roots of both sides. That leaves me with the absolute value of x is equal to 5, so x is equal to plus or minus 5. Again, plus or minus 5 means negative 5. In this particular example, segment RS and segment RT are tangent to circle Q. Find the length of segment RS. Notice we have a common external point, and both segments are tangent to the same circle. Therefore, we can state that segment RS is congruent to segment RT. Therefore, we can set their lengths equal to each other. Subtract n from both sides, subtract 1 from both sides, divide both sides by 2, n is equal to 4. Unfortunately, this is not our answer, because the question stated to find the length of segment RS. We will need to substitute the values in. 3 times 4, since n is equal to 4, is 12 plus 1, RS is equal to 13.